We experience the world in three dimensions: length, width, and height. These three dimensions are the fundamental building blocks of our physical reality, allowing us to navigate and understand the space around us. These dimensions define our physical space. They are the parameters within which we build our homes, design our cities, and create our art. Every object we interact with, from the smallest grain of sand to the tallest skyscraper, exists within these three dimensions. But there's another dimension, one just as fundamental: time. Time is the invisible thread that weaves through our lives, marking the sequence of events and the progression of moments. Imagine time as a fourth dimension, interwoven with the three spatial dimensions. This concept transforms our understanding of the universe, merging the spatial and temporal into a single continuum. This interwoven fabric is space-time. It's a dynamic, ever-changing entity that shapes and is shaped by the matter and energy within it. Space-time is not just an abstract idea, it's a tangible framework that scientists study and explore to understand the cosmos. It's the very fabric of our universe. From the smallest particles to the largest galaxies, everything exists within this space-time continuum. It's the stage on which the grand cosmic drama unfolds. Every star's birth, every planet's orbit, every black hole's formation happens within this vast, interconnected web. Every event, every interaction happens somewhere in space-time. It's the backdrop for all physical phenomena, the canvas on which the universe paints its story. Think of a stretched rubber sheet. This sheet represents space-time. It's a simple yet powerful analogy to help us visualize the complex nature of this four-dimensional fabric. Now place a ball on the sheet. The ball represents a mass, like a planet or a star. The ball creates a dip, a curvature in the sheet. This curvature is a visual representation of how mass distorts space-time. This is a simple analogy for how mass affects space-time. Just as the ball causes the rubber sheet to curve, massive objects like stars and planets cause space-time to bend, creating what we perceive as gravity. This bending of space-time is what keeps planets in orbit and governs the motion of celestial bodies. Mass warps space-time. This fundamental concept is at the heart of Einstein's theory of general relativity. Imagine space-time as a flexible, four-dimensional fabric that can be stretched and deformed. The more massive an object, the greater the warp. Just like a heavy ball placed on a trampoline creates a deeper dip, a massive star or planet causes a significant curvature in the space-time fabric. This warping is what we experience as gravity. Objects move along these curves, and this movement is what we perceive as gravitational attraction. Gravity is not a force acting at a distance. Instead, it's the result of objects following the curved paths in the space-time fabric. Instead, it's the curvature of space-time caused by mass. The more massive the object, the more it distorts the space-time around it. Imagine rolling a marble on the rubber sheet. The marble will naturally follow the curves created by the dips and bends in the sheet. The marble will curve around the dip created by the ball. This is a simple analogy to help visualize how gravity works in the context of space-time. This is similar to how objects move under the influence of gravity. Planets, stars, and other celestial bodies follow the curves in space-time. They are following the curves in space-time created by massive objects. This is why planets orbit stars and moons orbit planets. The Earth orbits the Sun, not because they are pulling on each other with an invisible force. Instead, the Earth is moving along the curved path in space-time created by the Sun's mass. It orbits because it's following the curvature of space-time created by the Sun's mass. This elegant explanation of gravity helps us understand the motion of celestial bodies in the universe. In 1905, a young and relatively unknown physicist named Albert Einstein revolutionized our understanding of space and time with a groundbreaking idea. He proposed the special theory of relativity, a theory that would forever change the landscape of physics. This theory rests on two fundamental postulates. The first postulate states that the laws of physics are the same for all observers in uniform motion, meaning that no matter how fast you are moving, the basic laws governing the universe remain unchanged. The second postulate asserts that the speed of light in a vacuum is constant for all observers. regardless of their motion or the motion of the light source. These seemingly simple postulates have profound implications that challenge our everyday experiences and intuitions. They tell us that space and time are not absolute entities, but are interwoven into a single continuum known as space-time. Space and time are relative to the observer's motion, meaning that they can change depending on how fast you are moving. One of the most startling consequences of special relativity is the phenomenon known as time dilation. Time dilation means that time itself slows down for objects moving at speeds approaching the speed of light. This effect has been confirmed by numerous experiments and has practical implications for high-speed travel and our understanding of the universe. For instance, atomic clocks on fast-moving aircraft or satellites tick more slowly compared to those on the ground. This is not just a theoretical prediction, but a measurable reality. The special theory of relativity has paved the way for many technological advancements and has deepened our understanding of the cosmos, influencing everything from GPS technology to our comprehension of black holes and the Big Bang. As we continue to explore the universe, Einstein's insights remain a cornerstone of modern physics, guiding us through the mysteries of space and time. Einstein wasn't finished. In 1915, he presented his general theory of relativity. This theory extends special relativity to include gravity. It describes gravity not as a force. Instead, it describes gravity as the curvature of space-time caused by mass and energy. General relativity predicted several phenomena. These include the bending of light around massive objects. It also predicts the existence of black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. Time dilation is one of the most mind-bending consequences of relativity. Time is not absolute. It flows differently depending on your relative motion and the gravitational field you're in. Imagine two identical clocks. One clock stays on Earth and the other travels at a high speed in a spaceship. When the spaceship returns, the clock that traveled will have ticked slower than the clock that stayed on Earth. This is not a mechanical error. Time itself has passed slower for the traveling clock. Time dilation has been experimentally confirmed. It's a real phenomenon. Section 6. Ripples in the fabric, detecting gravitational waves. General relativity predicted the existence of gravitational waves. Gravitational waves are ripples in the fabric of space-time. These ripples are produced by the acceleration of massive objects. Imagine two black holes spiraling into each other. This violent event would create ripples in space-time, propagating outward like waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made a groundbreaking discovery. It directly detected gravitational waves for the first time. These waves were produced by the merger of two black holes billions of years ago. Section 7. A universe transformed. The impact of space-time and relativity. The concepts of space-time and relativity have had a profound impact on our understanding of the universe. They have revolutionized our understanding of gravity. They have also provided us with tools to study the universe on its grandest scales. General relativity is essential for understanding the evolution of the universe. It's also essential for studying black holes, neutron stars, and other extreme environments. Space-time and relativity are not just abstract theories, they have practical applications. The Global Positioning System, or GPS, for example, relies on the principles of relativity to function accurately. Section 8. Unraveling the mysteries, open questions, and future explorations. While relativity has been incredibly successful, there are still mysteries to be solved. One of the biggest challenges is to reconcile general relativity with quantum mechanics. Quantum mechanics describes the universe at the smallest scales. These two theories, which are our best descriptions of the universe, seem to be incompatible at a fundamental level. Another area of active research is the study of dark matter and dark energy. These mysterious substances make up the vast majority of the universe's mass and energy. Understanding their nature could revolutionize our understanding of space-time and gravity. Section 9. Conclusion: space-time and the ongoing quest for cosmic understanding. The concepts of space-time and relativity have taken us on an incredible journey. From the depths of black holes to the vast expanse of the cosmos, they have revealed a universe stranger and more wondrous than we could have imagined. As we continue to explore the universe, new discoveries await, discoveries that will further illuminate the mysteries of space-time and perhaps one day lead us to a unified theory of everything.